This video we will starting to study the planar kinetics of a rigid body in terms of force and acceleration, and we have to starting with how to determine the mass moment of inertia. The mass moment of inertia is the property of the body that measures the resistance of the body to angular acceleration. Is the determination of the calculation for mass moment of inertia is same as the area moment of inertia that we have studied from the static. Okay, and the definitions of the mass moment of inertia is defined by the mass moment of inertia is equal to integrations of r squared dm. Okay, if we compare with the area moment of inertia, we change dA to dm. Okay, and the unit of the mass moment of inertia is kilogram meter square, okay, or slug foot square. Okay. So, as shown in this figure, the figures below show the mass moment of inertia formulation for two flat plate shape commonly used when working with three-dimensional body. And for the left-hand side, you see that is the thin circular dish. Okay, we have three axes, that is S, Y, Z. Okay, for the case of the rotation about X and Y, about axis X and Y, we have the same formula, that is 1/4 mr squared. That is, if we consider the rotation about this axis is like the flipping coin. Okay, so for the case that we consider the rotation of this solid about C axis. Sorry, it's not this. It should be this instead. For the case of about C axis, not C palm. Sorry. Okay. So for about C axis, this is like the rolling coin. This is the rolling coin. So same as the thin plate on the right hand side of the rectangular thin plate. For about X and Y axis, this is the flipping, and for about Z axis, this is the rolling. Okay. So, because the procedure for analysis of mass moment of inertia is very close to the area moment of inertia, but actually, if we derive the formula from the definition, we require the integration. Okay, that we have to subdivide it into the small element and integrate it. Okay, that is actually I will skip this detail. For more detail, you may consult with the textbook. Okay, and this is just some example from the text of Hibbeler. Okay, so we will skip to for the case that for the general solid shape, we already know the formula that is actually it comes from integration. But in engineering application, we normally use the general solid shape like this, that is like a sphere, cylinder, hemisphere, cone, and circular dish, thin plate, and thin ring, and also the cylinder rod. This general solid shape, we already have the formula. Okay, we will use this formula with the parallel axis theorem that we have learned from static. That is the topic of area moment of inertia. It is quite the same. Okay, you see that for parallel axis theorem for the case of mass moment of inertia is the same. We starting with the mass moment of inertia about the body mass center. Okay, it have to transfer the axis from the center of mass. Okay, like the area, that is, we have to transfer axis from the centroid. Okay, but this case, this is because it is a body, we transfer from the mass center. Okay, and is adding with the md square. M is the mass of the body, and d is the perpendicular distance between the parallel axis. Okay, so and the definition of radius of gyration same as the same as static. For the case of radius of gyration of the body, okay, it is defined by k is equal to square root I over m. Okay, as if we consider the composite body, we will apply the parallel axis theorem and sum up the mass momentum ratio of each part together. We will find the total mass momentum ratio of that body, of the composite bodies. Okay, let's take a look at this example. This example, the body is composed of the pendulum. It is a pendulum that is consists of the cylinder lock with a mass of 10 kilogram. This cylinder lock has a mass of 10 kilogram. And a sphere with a mass of 15 kilogram. Okay, the pendulum, we would like to find the pendulum mass moment of inertia about an axis perpendicular to the screen and passing through point O. We would like to find mass moment of inertia about this point. Okay, so we starting with we will apply the parallel axis theorem to these two bodies. That is, for the first one is composed of the lot. Okay, from the table we will find out the mass moment of inertia of the lot at its mass center is equal to 1 over 12 ml squared. Okay, so for the case of the lot, this is for the lot. Okay, the inertia, the mass moment of inertia of the lot is composed of the mass moment of inertia of the lot at the center of mass of the lot. Okay, that is 1 over 12 m. The mass of the lot is 10 kilogram. Okay, and the length of the lot is now is equal to 0.45 meter. Okay, square plus md square. D is now is from the mass center to point O, that is 225 millimeter. Okay, that's become 0.225 meter square, and then we get the mass momentum inertia of the lot. Okay, and then we move to the mass momentum inertia of the sphere. And we know that the mass momentum of the sphere at the mass center is equal to 2 over 5 mr squared. That is for sphere. We know that the mass of the sphere is equal to 15, and the radius of the sphere is equal to 0.1 meter. Okay, and then the distance from the mass center to the point O is equal to 450, adding with 100. Okay, so then it's become 550. Okay, that is equal to 0.55 meter. Okay, so then we have the mass moment of inertia of the sphere about point O now is equal to 4.598 kilogram meter square. Okay, and now we add two mass moment of inertia about point O together. We found the total mass moment of inertia here. That is complete this problem.